Hello everyone, my name is Colton Glick. I'm a junior in software engineering, and today I'll be talking about my research that I've been working on over the past year with the OpenUAS team as part of my Boeing Fellowship. To get started, we'll talk about what a UAS is. So a UAS, or Unmanned Aerial System, is an autonomous drone that is intended to fly research equipment or measurement equipment over a particular area. These areas can range from hazardous environments such as disaster zones to more commonly crop fields for collecting soil information. Generally, the idea is that it improves data collection while keeping lives safe and people out of dangerous situations. Currently, there's no affordable, fixed-wing, open-source UAS, and that's the hole that the OpenUAS team aims to fill. The OpenUAS team is a group of around 15 undergraduate students, including myself, and our main goal is to design and manufacture a UAS that is affordable, easily manufacturable, and easily repairable by users. That way, if a part breaks or if it crashes during flight, it can be easily fixed without having to wait around for parts to be shipped in. Now, I joined the electrical and software sub-team of the project, and so that'll be what the main focus of this presentation is on. To start, we'll talk about the hardware and software configurations of the craft. On the hardware side, we're using the Pixhawk 4, which is an open source flight controller and is relatively affordable at $196 for the model we're utilizing. Additionally, it comes with built-in sensors such as a gyroscope, an accelerometer, and a barometer, and allows for other sensors to be added to it that can be purchased elsewhere, such as a GPS, an airspeed sensor, a camera, and a rangefinder. It also runs the NUTX real-time operating system that's Unix-like. It prioritizes fast, efficient, responsive operations and provides a familiar environment for developers to work inside of. On the software side, we're using PX4 Autopilot, which is an open source software solution that is freely available for anyone to view, edit, download, and modify. It's intended for quadcopters and fixed-wing vehicles and is written mostly in C++. Now, within the PX4 software, each craft is defined by its airframe, which includes the number and location of control surfaces, propellers, and many other parameters. This is the main way that we can configure PX4 in order to customize it for our specific craft. It's also the main reason why we forked our own version of the PX4 software onto our GitHub repository. This allows us to directly program in the airframe into the source code of the software, making it easier for other users to utilize our tuned configurations. Our end goal is to integrate our custom airframe into the official version of PX4 or to distribute our own precompiled version. Another feature that I'm working to implement into the project is a simulated environment in order to test autonomous features and to train new pilots. To do this, we're utilizing the open source physics simulator known as Gazebo. Gazebo provides us a quick, safe, and cost-free way in order to test new features that are experimental and to train new pilots under manual flight. The way it works is PX4 is compiled and ran on a workstation computer in place of the Pixhawk 4. PX4 then communicates with an instance of Gazebo running on the same computer, keeping everything locally contained and fast and efficient. Additionally, I was able to develop a simulated environment of the airfield that we actually test at here in Ames. This allows for accurate GPS and elevation information inside the simulator when we're testing new features. This also allows us to create predefined flight plans that can either be executed inside the simulator or in real life without having to modify anything else. Currently, we're utilizing the default simulated vehicle that comes in with PX4. However, we're planning on switching this out for our custom CAD model of our vehicle that's currently being designed and iterated upon on our design sub-team. This generally allows for accurate flight simulation of the vehicle. However, each individual component of the craft needs to be accurately defined, including its mass, rotational inertia, and lift coefficients. Additionally, this semester, we wanted to improve real-time data collection in order to allow for autonomous landing and autonomous takeoff. Currently, PX4 utilizes a GPS and a barometer to estimate its relative altitude. To improve this, however, we added the Lightwear SF11-C laser rangefinder. This is mounted to the bottom of the craft and gives us an accurate distance measurement to the ground at any point in flight. This also gives us a range of 120 meters to 10 centimeters, making it perfect for what we're utilizing it for. The PX-4 already has a built-in autonomous landing sequence for fixed-wing crafts. By default, it utilizes a GPS, a airspeed sensor, and a barometer to estimate its location, altitude, and speed. Now, typically with this autonomous landing sequence, it's only possible to be used within a predetermined flight plan. However, adding the laser rangefinder allows us to execute this landing sequence without any predetermined flight plan due to the absolute nature of the distance sensor. Here's an example of some of the data that we would see coming out of the sensor. This is data taken from our most recent test flight. On the left is a manual takeoff, and on the right, a manual landing. We do notice there is a bit of an anomalous spike around the 30-meter area on the takeoff. This is due to the vehicle performing a roll maneuver after achieving altitude, and is somewhat expected due to the way the sensor is rigidly mounted to the bottom of the craft. However, if we look at the landing sequence, it's much more stable and consistent, so this issue is not much of a concern for our main use case. Like I mentioned earlier, we did perform several test flights of the UAS in order to determine its flight characteristics, perform autonomous sequences, and to measure our stall speed of our craft. The first flight of the OpenUAS happened in November 2020 and was hand-launched early in the morning. It was flown mostly in manual flight by John Edgren, and it was a bit unstable in manual flight. However, we were able to switch over to a stabilized flight mode, which utilizes the Pixhawk 4's internal IMU in order to create a feedback loop with the control surfaces and maintain stable flight while it's engaged. Unfortunately, the craft was hit with a gust of wind during one of our stall tests and spun out and eventually crashed. However, we were able to collect a lot of useful information from these flights, including the airspeed and stall speed. Here's a graph of the measured airspeed throughout the flight. We saw a max airspeed of 26 meters per second shortly after takeoff, and a stall speed of approximately 6 meters per second right before the spin out. We also measured the power statistics coming out of the battery for this flight. We saw a peak current draw of 120 amps during takeoff and during recovery maneuvers to pull out of the spin. Between this first flight and the next major flight of the OpenUAS vehicle, we also tested additional flights on a smaller RC plane known as the Apprentice. We tested stabilized flight modes as well as position modes, which is just generally different ways that the PX-4 can control the vehicle and respond to your manual inputs. We also tested predefined flight plans and confirmed our testing methodology for measuring the stall speed of the vehicle that we would then use on later test flights. We also attempted 2 autonomous takeoff and landing sequences with this craft and a smaller rangefinder. However, both of the autonomous landing sequences were automatically aborted by the vehicle due to a misalignment on approach. However, both of the autonomous takeoff sequences completed successfully. The second flight of the OpenUAS happened in April 2021 and featured an updated design with landing gear and a more efficient motor and propeller. This time, it took off from the runway and was again flown in manual and stabilized modes by John Edgren. The main goals of this flight were to test the performance of this improved motor and propeller selection, as well as to get a better idea of the stall speed from the vehicle. Unfortunately, we were unable to test autonomous landing, which was another goal of this flight, due to a similar crash during a stall speed test. Again, however, we were able to collect a lot of useful data from this flight. Our airspeed graph here can be seen. Here we recorded a max airspeed of approximately 27 meters per second, this time around the middle of the flight, and a stall speed of approximately 8 meters per second during those tests toward the tail end of the flight. This is similar to previous flights and is somewhat expected due to the minimal changes of the airframe body. However, if we look at our power statistics for this flight, we see a much reduced 62 amps for our peak current draw, again during takeoff and during a recovery maneuver towards the end of the flight, and an average current draw throughout the entire flight of 26 amps. This is significantly reduced from previous flights, which shows an improvement in the efficiency of the craft while maintaining a similar max airspeed and stall speed. Moving forward, we want to add some of these features to the OpenUAS, including obstacle avoidance. This would involve adding more rangefinders and possibly computer vision to the craft in order to identify and avoid obstacles during autonomous flight paths. This is currently being developed by Marcella Anderson, and I hope to join her in the coming semesters. Next, we want to improve the efficiency of the vehicle. Our current design is a little bit inefficient, using 268 watts on average. Improving this efficiency at all would generally improve battery life and allow for longer flight times. Finally, we want to improve our battery estimation methods. Our current method of estimating the battery is a little bit inaccurate, and it's not uncommon to see large voltage drops during intensive maneuvers cause the estimated battery remaining to vary wildly. In conclusion, during my time on the OpenUAS team, I've learned a lot about the PixHawk and the PX4 software, how to manage it, how to configure it, and how to modify it to fit the team's needs and goals. Additionally, I learned how to create a synthetic environment and aircraft in order to test autonomous features and to train new pilots inside of a safe, efficient environment. Finally, I learned the basics of aerospace engineering and the terminology used inside of the industry. I plan to contribute to the team next year as the electrical and software sub-team lead and to improve the software solution even further. That's the end of my presentation. I want to give a thank you to the Boeing Company, Dr. Rosier, and Iowa State University for allowing me to explore this field. Thank you.